Welcome, curious minds, to the deep dive. Today, we're plunging into the very foundations of our modern world.
Hmm.
I mean, literally.
Concrete.
It's everywhere.
It really is. And here's a fact to get us started. Concrete is the most widely used construction material on the planet. Think about this. About 1 ton consumed per year for every single person.
That's an astounding figure. It really puts the scale into perspective.
It does. And for too long, figuring out its environmental impact, especially CO2 emissions, has been, well, a bit murky, hasn't it? Lots of guesswork.
Exactly. More conjecture than hard data sometimes. So that's what this deep dive is about, cutting through that guesswork.
Right. Our mission here is to give you the solid data straight from quarries, from manufacturing plants. Basically a shortcut to understanding concrete's actual greenhouse gas emissions. No more speculation.
We're going to break down exactly where the CO2 comes from in concrete production and, importantly, explore some surprising ways to cut those emissions. And stay with us because there's a really crucial aha moment coming later about what truly makes a building sustainable over its entire life.
Yeah, it's about looking beyond just the materials sometimes.
Okay, let's get into it. The primary sources of concrete's emissions. When you look at a typical mix, what's the main driver? Where's most of that CO2 coming from?
Okay, so the big one, no surprise really, is Portland cement. It is overwhelmingly the primary source. We're talking 74% to 81% of the total CO2 emissions in typical concrete mixes.
Wow, 3/4 or more just from the cement.
Exactly. And what's fascinating is how that breaks down. Roughly half of those cement emissions are purely process-based. It's the actual chemical reaction, limestone, KCO3 being heated in the kiln and breaking down into lime, CaO, and CO2.
So that CO2 is released regardless of how you power the kiln.
Precisely. It's inherent to making cement clinker. The other half roughly comes from the energy used the fuel burn to heat that kiln to incredibly high temperatures, plus the electricity for the plant operations.
Okay, so process and energy.
Yeah. And the study calculated an overall emission factor for cement, including getting it to the batching plant, of about 0.82 tons of CO2 equivalent per ton of cement.
Right, 0.82, that's a key number. Now, cement clearly dominates, but what else is contributing significantly? I mean, 80% is huge, but there's still another 20% or so.
Good point. After cement, the next major source is the coarse aggregates, the gravel or crushed stone. They contribute roughly 13% to 20% of the total CO2.
Okay, and where are those emissions coming from? Is it digging them up, transporting them?
Well, that's the interesting part. The vast majority, typically around 80% of the aggregate emissions, comes from the electricity used in the crushing process.
Breaking big rocks into smaller rocks takes a lot of power.
A massive amount. Think about the energy needed to run those crushers continuously. For example, the study found numbers like 0.036 tons of CO2 per ton for basalt aggregate and maybe 0.046 for granite. It varies a bit depending on the rock type.
And what about the blasting? Using explosives must have a big footprint, right?
You'd think so because explosives themselves have high emission factors, but they actually contribute very little overall, less than 0.25% to the aggregate emissions.
Really? Why so low?
Simply because you use tiny quantities for the blasting itself. So yeah, blasting, digging it up, hauling it around the quarry, transporting it offsite, all that together is less than a quarter of the emissions from coarse aggregates. The big energy hog is the crushing.
So if you want to make aggregates greener, you really need to focus on that crushing stage.
That's the main lever, exactly. Maybe smarter blasting techniques to get smaller initial fragments or just, more efficient crushing machinery, better maintenance. Lowering that electricity demand is key.
Okay, that covers the coarse stuff. What about the fine aggregates, like sand? Are they similar?
They generate significantly less CO2, maybe only 30% to 40% of the emissions compared to coarse aggregates. Concrete sand, for instance, was around 0.014 tons of CO2 per ton.
And why the difference?
It's simpler processing. Fine aggregates are generally just graded, sorted by size. They aren't typically crushed in the same way, which saves a lot of energy. Their emissions are kind of split between diesel fuel for the extraction and transport and electricity for things like pumping water and running the grading equipment.
Right. And then there are the other bits and pieces. Admixtures, the batching process itself.
Yeah, we looked at those too. Admixtures, those chemicals added for specific properties, their contribution is negligible, really tiny amounts.
Right.
Same for the actual concrete batching at the plant, mixing the cement, aggregates, and water. That's only about 0.00033 tons of CO2 per cubic meter. Transporting the mixed concrete in the trucks is also pretty small, maybe 0.0009 tons per cubic meter. Even placing it on site, like pumping it up
All
floors.
quite minor in the grand scheme of things.
Exactly. They're just not significant compared to producing the cement and the coarse aggregates.
So putting it all together, what's the bottom line for a standard cubic meter of concrete made just with Portland cement? What's our baseline footprint?
The study found that for typical normal strength concrete mixes, using only Portland cement, you're looking at somewhere between 0.29 and 0.32 tons of CO2 equivalent per cubic meter.
Okay, around zero point 0.3 tons per cubic meter. That gives us a solid benchmark.
Definitely. Now we know where the emissions come from, we can talk about how to reduce them.
Perfect transition. Let's move into those strategic reductions. You mentioned supplementary cementitious materials, or SCMs. Tell us about those.
Right. SCMs are basically materials, often industrial byproducts, that can replace a portion of the Portland cement in the concrete mix. This is a key strategy because cement has such a high footprint.
So using less cement by substituting something else in.
Exactly. And the study looked closely at two common ones. First, fly ash. This is a fine powder left over from burning coal in power plants.
Okay, a waste product finding a new use.
Precisely. And the data showed that replacing 25% of the cement with fly ash can cut the concrete's total CO2 emissions by about 13% to 15%. Its own emission factor is quite low, around 0.027 tons of CO2 per ton, mostly from processing and transport after it's produced.
13 to 15% reduction just by swapping out a quarter of the cement. That sounds pretty good.
It is, and it's widely used. The other major SCM studied was granulated blast furnace slag, or GGBFS.
That comes from steel making, right?
Correct. It's a byproduct of the iron and steel industry. And GGBFS was found to be even more effective in some ways. Replacing 40% of the cement with GGBFS could reduce the concrete's CO2 emissions by about 22%.
22% reduction. That's quite a jump from fly ash.
It is. Now, interestingly, the emission factor for GGBFS itself is actually higher than fly ash. It's around 0.143 tons of CO2 per ton.
Hold on, that seems backwards. If GGBFS has a higher footprint than fly ash, how does it lead to a bigger overall reduction in the concrete's emissions?
That's a really important point, and it highlights the nuance here. The key is the percentage of replacement you can achieve.
Okay.
While GGBFS has a higher individual factor, you can typically replace a larger proportion of the Portland cement with its, say, 40% or even more in some mixes without negatively impacting the concrete's strength or durability too much. Fly ash is often limited to lower replacement levels, like that 25%.
I see. So even though GGBFS is slightly more carbon intensive itself than fly ash, because you can use more of it to replace more of the really high emission cement, the net effect on the final concrete mix is a larger overall CO2 saving.
You've got it. It displaces more of the main culprit, leading to a bigger total reduction. It's about optimizing that blend.
That makes sense. So we understand the sources. We see how SCMs can make a real difference at the material level. But how does this fit into the bigger picture of a whole building?
Right, context is crucial, and the study included a fantastic case study to illustrate this, the K2 Public Housing Project in Melbourne, Australia.
Ah, yes, I remember reading about K2. It was quite innovative, wasn't it? Designed for a super long life, like 200 years, aiming for on-site renewables, low water use.
Exactly. A real showcase of environmentally sustainable design, or ESD. They incorporated things like maximizing solar gain in winter, passive ventilation to reduce cooling needs, solar panels on the roof, using the building's thermal mass effectively, plus selecting low-embodied energy materials, which is where our concrete discussion fits in. They even had solar hot water and water recycling systems.
A very holistic approach to sustainability. So how did the numbers stack up when looking at its lifetime emissions? Let's start with the operational side, running the building day to day.
Okay, so predictive models were used to estimate the likely operational energy consumption. This covers lighting, elevators, hot water systems, and crucially, the plug loads from residence appliances. The estimate came out to around 850 tons of CO2 equivalent per year.
850 tons a year, and over, say, a 100-year time frame.
You're looking at a total of 85,000 tons of CO2 equivalent just from operating the building over a century.
Wow. Okay, 85,000 tons. Now, let's compare that to the concrete's contribution, the embodied emissions locked in from the start. K2 aimed to use fly ash, right?
Yes, the target was to replace 30% of the Portland cement with fly ash in the structural concrete. Based on the emission factors we discussed, that substitution alone was estimated to save about 206 tons of CO2 equivalent compared to using concrete made only with Portland cement.
206 tons saved up front. That's not insignificant.
No, it's a definite, quantifiable saving achieved during construction. But now comes the really interesting part, the aha moment.
Okay, I'm ready.
When you compare that embodied carbon from the concrete the initial hit to the lifetime operational carbon, the study found that the CO2 generated by producing all the structural concrete for K2 will likely be less than 1.4% of the estimated total CO2 emissions generated by just operating the building over 100 years.
We'll say that again, less than 1.5%.
Less than 1.5%. The emissions baked into the structure are tiny compared to the emissions from running the building year after year.
That really changes the perspective, doesn't it? It puts the focus squarely on how the building performs over its life.
Absolutely. And consider this. The energy-efficient design of K2, the passive ventilation, the insulation, the solar aspects that design is estimated to cut operational energy use by 57% compared to a standard building of the same size.
57% reduction. What does that mean in CO2 savings per year?
It means saving approximately 1,125 tons of CO2 equivalent every single year.
1,125 tons a year, compared to the 206 tons saved once by using fly ash in the concrete.
Exactly. Over that 100-year period, the savings from the efficient design are roughly 500 times greater than the savings from the low-carbon concrete choice.
500 times. That is staggering. So the big takeaway here.
Well, it strongly suggests that while choosing lower embodied energy materials like fly ash concrete is definitely valuable and provides real immediate benefits, the strategies that improve a building's operational energy performance, those passive design measures, they have the potential for a vastly greater impact on reducing total greenhouse gas emissions over the building's entire lifespan.
But there's a nuance there too, isn't there? Operational savings depend on how people actually use the building.
That's a critical point. Operational savings rely heavily on assumptions about tenant behavior, appliance efficiency over time, even climate changes. They can be harder to guarantee. Whereas the embodied carbon savings from material choices, like using SCMs, are locked in and quantifiable from day one.
So you need both, but the scale of potential savings from operational efficiency is just immense.
Precisely. And it also underscores the need to look at the whole picture when comparing materials, not just cement versus steel, but the entire concrete mix, and more broadly, the entire building system and its lifetime performance. A holistic view is essential.
Okay, so we've really unpacked a lot there. We started with the basics of concrete's footprint, identifying cement and coarse aggregates as the main culprits.
Yeah, and then we explored how SCMs like fly ash and GGBFS offer practical ways to reduce those initial embodied emissions quite significantly.
But the K2 case study delivered that powerful insight. The huge leverage available through smart passive design that slashes operational energy use over the building's lifetime.
Right, that comparison between embodied and operational emissions really puts things in perspective. It shows where the biggest long-term gains might be found.
It certainly challenges us to think more holistically about sustainability in construction, and perhaps beyond. It makes you wonder, what other hidden impacts are we over or underestimating in the things we build and use every day?
That's a great question to ponder. What really stands out to you listening to this that might change how you view the buildings or the infrastructure around you? It really highlights that sometimes the most impactful changes aren't the most obvious ones initially.